here's the solution to this example. The first thing that you should notice is that all of the atoms have the exact same number, or all of the ions have the exact same number of electrons. Ions and atoms that have the same number of electrons or identical electron configurations are known as isoelectronic. So calcium 2+, potassium+, Cl- and S2- are isoelectronic to one another. The difference between these four ions are the number of protons. Calcium has 18 electrons and 20 protons. Potassium 1+ has 18 electrons and 19 protons. Cl- has 18 electrons and 17 protons. And S2- has 18 electrons and 16 protons. Since S2- has 2 more electrons than protons, those protons aren't going to pull very efficiently on those outermost electrons. So S2- should be the biggest of all 4 of these ions. Cl- should be the second one because it only has 17 protons pulling on its 18 electrons. Next, when you look at K+, it has 18 electrons but 19 protons. So the 19 protons will pull more efficiently on the 18 electrons in potassium than the 17 electrons will in Cl-. So K+ should be smaller. Finally, Ca2+ should be the smallest. It has 18 protons, or 18 electrons, but 20 protons. The next periodic trend, the third one that we will look at today, is ionization energy. That is the energy required to remove a valence electron from the ground state of a gaseous atom. Let's say that we want to make potassium 1+. Now, what we must do to determine the ionization energy for losing that 1 electron is convert potassium solid to a gas and then remove 1 electron. That is known as ionization energy. So, a chemical equation representing the ionization energy for potassium in its gaseous state is K gas yields K plus gas plus 1 electron, and its ionization energy, denoted by IE, is plus 419 kilojoules per mole. Since energy is required to remove an electron from an atom, the process is endothermic. That means the sign of the ionization energy must be positive, and you must put energy into the atom to get rid of the 1 electron. Now, when we look at forming something like a 2+ cation, we must remove 2 electrons from something like calcium. So when we convert calcium gas to calcium 2+, we must do it in 2 steps. First, convert calcium gas to calcium 1+ gas by losing an electron. And that has an ionization energy associated with it of positive 590 kilojoules per mole. In the second step, we take calcium 1+ from our first step and remove 1 more electron, making calcium 2+ gas. It also has an ionization energy associated with it of 1,145 kilojoules per mole. Now, calcium commonly forms a 2+ cation. Ions with charges greater than 1 must have a series of ionization energies associated with them. IE1 is known as the first ionization energy, and IE2 is called the second ionization energy. So that brings up a question. Why does it require more energy to remove the second electron from calcium? Think about electron configuration and effective nuclear charge. When you form calcium 1+, you now have 19 electrons and 20 protons. That means that the effective nuclear charge, the amount of positive charge that the remaining 19 electrons sees, is increased because it has one less electron to pull on. So it's going to take more energy to remove that second electron. This table shows the ionization energies for the first 20 elements. Notice, and we'll pick out calcium to look at, that when you remove the first electron, that normally takes the least amount of energy. Then you remove the second electron, and that requires more energy. When you take out the third electron, that requires a lot more energy. Removing more and more electrons means you're removing more, or requires more energy. Why? 2 reasons. After you remove the first 2 electrons in calcium, you have emptied out the 4s orbital. You must start removing electrons from the 3p orbital at that point. That means you must use a lot of energy to break up an ion that has an electron configuration equivalent to a noble gas. So anytime you see a tremendous increase in ionization energy between one electron and its second electron, or another electron, that means you are penetrating and removing an electron from the noble gas core. If we look at potassium, it requires only 418.7 kilojoules to remove the first electron from potassium. But to remove the second electron requires over 3,050 kilojoules per mole. One more example. Let's look at aluminum. To remove the first electron in aluminum requires 577.9 kilojoules. To remove the second electron requires 1,820 kilojoules. The third electron requires 2,750 kilojoules per mole. But when you break in and try to remove that fourth electron to form aluminum 4+, it requires 11,600 kilojoules per mole. That means to remove that fourth electron, you are breaking the neon noble gas core.